Yeah, well, it's an honor to be speaking here, especially after this special session. And I would like to thank the organizer for having set up this great conference so far, and yeah, very polite conference at that. So I'll be talking about work that from last fall. The general context is we trying to study N-Course Spur-Yang mills as a toy model for four-dimensional field theory, AdS, supergravity, string theory. So it's a toy model that's a bit different from the other toy models that have been discussed so far, in that I believe it will be very simple once we understand it fully, but right now it's still more of a laboratory where we can test new tools than something that has been solved. So in this talk, we'll be exploring a kind of a new corner of it. We'll be focusing on the supergravity limit, so strong coupling. And we'll be studying correlators, so correlation function in CFT that are dual to various scalars-Klein modes on AdS5xS5. One basic motivation for that is to go beyond the planar limit, where we've seen that. So the planar limit, many of you know, there's the spectrum, for example, has been solved using the quantum spectral curve. A lot of development there. So we're trying to peek beyond that. And KK modes are interesting for their own right. For example, if you want to understand from the CFT side why the dual need to have extra dimensions, we better get to understand these modes. So they have to run in loops, and that's the sort of thing we try to compute from the CFT side. So I'll give this talk backward, starting by this abstract by a paper by Warren Siegel, where they found that there was a way of writing. Okay, they observed that the AdS5xS5 is a conformally flat space, which is amusing, and they observed that this allowed them to write the propagator in a way that looked almost identical to 10-dimensional flat space. And they deduce from that probably AdS CFT calculation will be much simpler if we don't do a mode expansion. So what I'm going to tell you about is, well, this dream is something that we're going to fulfill for 4-point correlators. We're going to manage to talk about all of the 4-point correlators without doing mode expansion. So that's one of the main results. I can even tell you the recipe in 30 seconds. So you take the lowest scalars-Klein mode, which in the CFT is like the stress tensor or the dilaton, the same multiplet. And it has a 4-point correlation function that has been computed 20 years ago. And now, if you want to know what the KK modes do, just take each of these 4-dimensional distance and add some 6D distance to it. And then series expand in Y to get more and more powers, higher powers of Y to get higher KK modes. That's all. All the KK modes are in that slide. So, okay, I want to explain. Okay, I'm going to give some moral reason to this at the end of the talk. The reason I put unreasonable in the title of the talk is that I don't have a complete explanation. I'm just going to give some moral reasons. But for the bulk of the talk, I want to explain why it took 20 years before we can, confidently make such assertions. Why do we have now the tools to make such calculations? So part of the talk will be about the calculation techniques. Then I explain exactly the result. Somehow there's some kind of conformal symmetry that you can exploit about 10D supergravity. And I discuss some generalization. Okay. Okay, so Feynman diagrams and supergravity are hard. In AdS, it's even harder. We're not going to do that. What we're going to do is try to break this calculation of correlation function into physical building blocks. And okay, so I picked this slide from Zvi's talk because the spirit of what I'm going to do is very similar to this sort of cutting rules that are widely used in scattering amplitudes. Perturbation theory to build loops from trees and trees from simpler trees. So of course in AdS, so the rule of the game is to make physical things where you have on-shell propagators. And of course in AdS, when you put something on shell, it means it goes to the boundary of AdS. So of course, you're going to get to draw a little circle around each of these diagrams, meaning that they are written diagrams now. So will be really any way of breaking a AdS calculation into physical building blocks really has to be something that you do on the CFT side. Okay. So what's the theory on the CFT side? So we're talking about n equals 4 triangles. We're taking a limit of large n and strong coupling. So the input are the symmetries. And the only input about the dynamics that we'll need is that basically all the operators go away. They acquire large dimension. They get lift up. That's all you need to know from AdS CFT in this talk. And the only operators which survive, it's kind of a minimal spectrum. They are the ones which are protected. They're forced to be there. And this operator can be interpreted as the stress tensor and various spherical harmonics of the graviton and its super friends. So these are the light operators that we have. We have multi-traces product of them. So our goal is going to be to compute all the 4-point correlator of any of these KK modes at 3 level and eventually loops. So that's the goal of this talk. Okay, the tool we're going to use, so there are various tools we can use. I'm going to introduce you to the one I like. But the ingredients that go into it are the ingredients that anybody has to use. So I'm going to use this inversion formula, and what it does is it gives you the OP data. So we're in the CFT, so the OP data completely fixes the theory. And it's an integral representation, so we have to, there's something that's fixed by group theory, and we have to integrate over the coordinates of this correlation function. So an object that, called the double discontinuity, that has an interpretation as the absorptive part of the diagram. And what this does is that it's a bit like it's literally a Kramers-Kronig relation. In AdS, it allows to reconstruct the correlator from its absorptive part. And the point is that this is literally going to be a sort of cutting rule where the right-hand side is simpler to compute than the left-hand side. Okay, let me briefly explain the intuition behind what's this absorptive part. So it's something that's really Lorentzian. So if you put 4 operators with time going up like that, you can loosely think of this as a scattering process where 1 and 3 scatter and end up at 2 and 4. And if you think of this as a scattering process, then this correlation function is like the amplitude, which is like a unit part plus a connected part. And the absorptive part in this context, we know what it is. It's the imaginary part of the amplitude. And if you play this game, well, to get the imaginary part, you need the complex conjugate. But in fact, you need something else. You need something that's like the unit. I'm not going to explain what it is, but it's basically something with the operator ordering. And if you combine these 3 things to extract the imaginary part of the amplitude, you find that the combination you need is exactly this double commutator. So there's a natural absorptive part of a correlation function. This is double commutator. It has very nice properties. For example, it's positive, it's bounded. It's been used in important works a couple of years ago. So these properties, as well as some analytic properties, were the key to proving the bound of chaos and one of the proof of the ANEC. So somehow this encodes these properties of this object encode somehow unitarity and causality. And this is the ingredient that go there. But of course, causality implies something else. Causality is the reason why forces come from particles. It's the reason because we can't have instantaneous action at the distance. And this is what this other formula makes manifest, that interaction comes from particles. So let's see that this absorptive part comes from particles. So the point is that this double commutator, it kills, when you do the OPE, it kills many terms. And the simple way to see this is if I take the OPE between 1 and 4 here, okay, I get a sum of powers, and the powers are fixed by dimension analysis, where delta is the dimension of the intermediate thing. And if you want to compute the commutator, well, nothing very wrong happened when you go time-like. It's just that this picks a sign, so because of the I epsilon, you get some phase. So the commutator is proportional to the sign. And in the CFT, you always have especially at large n, you always have double trace operators. But these double trace operators have integer exponent. So the sign is 0. In fact, the sign is proportional to the enormous dimension, which is the 1 over n square correction. So the double commutator is in fact 1 over n square, which is a one loop effect. And in fact, you can precisely define this cut picture to be this square of an enormous dimension. So if you calculate this double commutator at tree level, you find that it throws away all the double trace in the Witten diagram and just gives you one single trace. And a single trace, that's a single conformal block we can draw as a product of two 3-point functions. So this imaginary part is successfully breaking the process into simpler bits. So that's what we're going to use. So to summarize, we've identified this absorptive part that simplifies the process, and then we're going to feed this into this Kramer-Kerny relation to get the amplitude we care about. And once we have it, in principle, we can keep going and get one loop from squaring trees. Kind of a bootstrap spirit. Okay, let me briefly review some developments about this formula. So you have to do an integral over some causal diamond of a block times, and if you put some cross-channel, if you use the OP in the cross-channel, you have to integrate a block against a cross-channel block. So the basic integral is something like a pairing between a block and a cross-channel block. That's called a 6J symbol. You can count, because there are like four labels for the external legs and 2 internal ones, so 6 J's. Here, the group is the conformal group. So it's not like the Virasoro group. It's much more, it's a much simpler thing than for Virasoro. But still, it's more complicated than like, this is surprisingly complicated. In d equal 2, d equal 4, there are some explicit expression in terms of 4f3s that people have obtained. In general dimension, I'm not aware of analytic formulas. There are some limits where you can do this integral. For example, if you take large spin, that's going to push the integral to some corner, when that's a so-called double Lycone limit. And if you expand the integral in that limit, you reproduce sort of asymptotic expansion that Agnesi, for example, has been discussing. There's been some interesting other resummations that have been done in the last year. So at leading twist, we can get exact formula. For this talk, in 4 dimensions, so we could use this explicit expression. But in fact, in n equals 4 is always simpler than everything, because the external dimensions are protected. We have these half BPS operators with integer dimension. All the integrals just give like boring gamma function. The integrals are really simple for n equals 4, which is, again, the point of studying n equals 4. Okay, let me say briefly one of the tools we use. Okay, we have to account for the supersymmetry because it helps our life. The way to do this is to use the word identities, which basically break the correlator into 4 parts. And here I just want to make briefly an analogy. This part here that's not protected, the last line, it's kind of the one that's going to be caring about. And it's roughly as a form that's something that you can interpret as like a SUSY delta function times something that's going to be like the 1 over STU part of the supergravity amplitude. And let me also briefly mention that this is some Carroll part here, that's a protected part of the amplitude. The fact that it's protected is not particularly important for us. We can apply the one-dimensional inversion formula that Witten, Stanford, and Simon Stuffen derived to this function. We can reconstruct it completely. And we do the whole calculation in strong coupling, and we check that the non-realization theorems work. It matches with CAP. Something which is nice about the supersymmetry here is that one has to ask when this Kramer-Kerny relation converge. Are they subtractions? Are they things like that? Here, normally it converges only for j greater than 1, but supersymmetry buys us 4 units of spin. So it converges for j greater than -3. So the UV behavior is excellent. That means that we effectively get convergence sum rules that extract the stress tensor in one channel from stuff in the other channel. So these are a bit reminiscent of the convergence sum rules that Sasha talked about, also that these gentlemen derive. It would be interesting to make the connection more precise, because the point of supersymmetry is that it's relating the scalar stuff to the stress tensor, the stuff with spin. So maybe there's a version of that which works directly for anything with spin. That would be interesting to study in the future. Okay. So we're going to apply this formula. Let me just briefly go to an example. Okay, so the simplest correlator is 2222 is a 4 stress tensor multiplets. To compute its imaginary part, or absorptive part, there's only one cross-channel block which contributes. You can exchange stress tensor. And you take the stress tensor block as some hypergeometric function. Its discontinuity just comes from a pole, so it's that expression. That's the only input we need. It may feel a bit unintuitive that a pole has a double discontinuity. But if you write cross ratio in terms of the coordinates, and recall that you're supposed to be computing a commutator of 1 and 4 and 2 and 3, it makes sense that there's a double discontinuity there. So anyway, given that expression, what you can do is you feed it into the inversion integral, and you get the OP data, which is the correct result. Something else you can do is you can try to kind of reconstruct the function of cross ratios of coordinates. It's the unique function with the following properties. Basically, its double discontinuity has to be this, and that way you can uniquely reconstruct the known supergravity result from 20 years ago. Okay. So with this tool, with this machinery, we started looking at correlators of KK modes. For example, if you have a fourth mode here, then okay, you can exchange 2. If you have the cross channel, you can exchange say 2 and the fourth one. In general, when you have many KK modes, so here we're going to be interesting. What we extract is the OP data for the double trace in the direct channel. And if you have a double trace with O2 times O4, it can mix with O3 times O3. So what we extract in the CFT are the dimensions of operators and the OP coefficient. And here there's mixing, so already what we extract is a matrix of anomalous dimension. So we compute this matrix and some number here. And then, okay, of course, what you do is you diagonalize the matrix. And amazingly, you get pretty eigenvalues. It's all like rational functions. This delta is some polynomial. So you keep going, and then you look at some case where you have some 4x4 mixing matrix. And it's a dense matrix. This is a complicated matrix. But you compute its eigenvalues, and you get beautiful rational numbers. I don't know if it ever happened in your life. You diagonalize a 4x4 matrix and get rational numbers. It's not supposed to happen. So this was observed just a little bit before by other people, by this gentleman, before we put out a paper and we confirmed the conjecture. So the rest of the talk is going to be about explaining how this madness came about. So effectively, you can replace AdS5xS5 by a flat space and get the answer. So here's the proposed symmetry explanation. So basically, right, if a matrix like that gives you something rational eigenvalues, it has to be that there's some group theory explanation, that this matrix is just building up some Clebsch-Gordon coefficient or something of some group. So here's the symmetry explanation. So as mentioned in my first slide, AdS5xS5 is conformally flat. You can very easily see this in Poincaré coordinates. And okay, what's it good for? Because obviously gravity is not conformal. So we have gravity in AdS5xS5. So what does it buy us? Well, if you squint at the supergravity amplitude, you can write it, so it's G Newton times some SUSY delta function times 1 over STU. Well, G Newton times delta 16Q is actually dimensionless. So 1 over STU is actually, as the correct unit, to be a conformal amplitude in 10 dimensions. That's a funny coincidence. So somehow that's what we're going to be, that's going to be the explanation of the magic we see. So here's some of the manifestation of this symmetry as far as the 4-point correlation function go. So, okay, I told you the eigenvalues are rational. They're not just rational, actually there's a logic to them. The eigenvalues are equal to this, okay, the sum factor of energy times some Pochhammer of 6 Pochhammer of spin plus 1. In fact, you can compute you can do something very dumb in flat space. You can take 1 over STU and expand it over spherical harmonics and ask what the coefficients are, and the coefficients are precisely that. And if you take this coefficient, 8 pi g Newton, you convert it to center charge and string units, you get precisely this formula. And on the other end, the anomalous dimension was given by this. And you see that the formulas nicely match. In fact, even the factors of 2 make sense. This is some kind of 8th order Casimir that matches with energy to 8. It just works, it just matches on the nose. So the flat space phase shift is exactly the anomalous dimension. There's some offset in this formula, which you can understand because if you take irreducible representation of SO12, you break it apart into SO6 representations, you get some offsets. So actually an infinite sum, so you can even understand the offset and the multiplicities. That's interesting. Sort of the punchline is this symmetry is combining various, it's resolving the mixing problem, so it's combining all the correlators together. So you can actually use the symmetry to package all the correlators together. And the trick is you make this 10-dimensional object. That's a function of 10-dimensional distance. It's a correlator of dilatons. Now here you have to do a bit. Okay, it's not here yet. Okay, let me explain a bit this formula. So this is supposed to be a generating function of all spherical harmonics, and the way it works is that different powers. Let me step back here. So the way it works is that each of the y's is like a null 6 vector that you dot into these tensors just to make them to absorb soak up the indices. So if you take the quotient of that, that's homogeneous in the y's. That's a given correlator. And you can write down the contour integral formula, which extracts the nth term in this Taylor series expansion. And that's the general formula, which gives you any KK mode you want. If you evaluate it in practice, what it predicts are differential relations. And you can check this relation against results that are 15 years old. It just works. The pattern was not noticed, but it just works. Okay, I just want to say it's a bit tricky the way it works. You have to take this Casimir and S4. You have to cancel. You have to wave your ends a lot to really, you wouldn't be able to make this conjecture if there wasn't data. But if you fudge around, then you can make a good guess, and eventually you land on it. So in summary of this, we have. So in this work, we've used the inversion formula to compute correlators. We found the symmetry. The symmetry explains the double trace mixing. Using the symmetry, we can also explain a nice formula that was obtained 3 years ago for all the correlation function in momentum in Melian space. This formula was compared successfully with supergravity Witten diagrams. Basically, all the approaches agree, so that's great. Let me briefly mention further implication. So we can explain, if we take the Melian transform in this generating function, you automatically get this nice formula by Rastelian Zoo. It was a conjecture, but now the proof is reduced to essentially a group theory statement, which we haven't really proved, but my attitude about group theory statements, if you check them to high order and you have a lot, then it's just true. Physicist induction works in this case. And the other nice thing that I want to elaborate slightly on is that basically using 10-dimensional symmetry, we've diagonalized all the mixing problem. So we can compute sum over all the KK modes running in a loop just by putting it in the block. Let me elaborate slightly. So we have prediction even for like summing of the ladders, at least the leading logarithmic part of each ladder. So that's one bit of information about our loops that we have. So you take this very simple function, you hit it with 11 derivatives, and you get the function. Okay, there's been a generalization recently to AdS3 cross S3 cross K3 by this gentleman. AdS3 cross S3 is also conformally flat. You have half the supersymmetry in this example, which is exactly what you need so that this factor is dimensionless and this amplitude. So basically the same argument work in that case, and that package all these 3 harmonics, at least for some correlators, not all yet. And okay, I'm almost out of time. I want to briefly mention something. So what we use so far is the conformal symmetry of 1 over STU. You can ask, okay, that's supergravity. What about string corrections? So, okay, string corrections have been calculated. So Agnese, VC, discussed this. And for some tool, you can use, for example, flat space limit plus 2Z localization. You can completely fix them. And this is for 2,2pp. And you look at this, and you don't necessarily find enough pattern. There's nothing very obvious. But something amazing was found 2 weeks ago. When you look at when you again diagonalize this OP data and look at this, they found that this thing is exactly diagonal in the same basis that the 3-level amplitude is diagonal. And it only affects the 10-dimensional spin equal to 0, or 2 for the next correction. So I think it's very suggestive that there's going to be a way to package the alpha prime corrections into some kind of generating function. So yeah, thanks for your attention.
So questions, comments?
You mentioned that you can compute these letters. Can you resum them and see the equalization or something?
Yeah, I haven't yet been thinking about it. I know that James Raman has been thinking about that. So this is only the leading cut of the ladder. So you'll get really something like the iconal. Yeah. But from the viewpoint of the OP data, it's just exponentiating the anomalous dimension in that channel. Yeah.
Could I ask a quick question?
Yes.
You talked about the correlation function of 4 operators.
Yes.
Is there any generalization to higher point functions?
So the 5-point amplitude has been available for about a month. So it's only the 2222 case. And again, I think it's a case where there might be something. In fact, it's a bit strange. So there are some word identities that these 5-point amplitudes satisfy that are reminiscent of the conformal word identities. I think it will take some time to look at them, but maybe if one look at them the right way, it could be that yeah, we don't know yet.
So the last line on the slide seems to imply that you think this approach might work for AdS4 or AdS7. Can you elaborate on that?
Well, the argument I presented will definitely not work for AdS4 cross S7 because it's not conformally flat.
But then what does this last comment about less conformal looking theories mean?
Well, nobody is stopped to look for patterns. I think it will be much more interesting if something like that holds in these theories than No, but I think the string correction of it's very surprising because the string correction they're also not conformal in any obvious sense, and yet they seem to follow the same organization principle. So I think, it does seem that there's a bit more under the hood than the explanation I've given you so far. So I think it's worth looking at other cases.
Have you or anyone else looked at the AdS2 times S2 case? That would seem simpler, that's less dimensions.
Nope.
Any further questions? Right. If not, let's thank the speaker. So the next speaker is Pedro Vieira. He's going to talk about octagons.
Is the microphone in? Yeah. Thanks a lot for the invitation to this very nice city. It's my first time here. I had a great walk yesterday. So thank you very much for putting up this very nice conference. So I'll be talking about octagons. And here is an octagon. You see it has 8 edges. The outer one is also an octagon, but these edges are very small, so it looks more like a square. And it's often the case that my octagons will look more like squares because 4 of the edges are very small, as we are going to see. But don't be fooled. Both are octagons, this one, and they are both equally good. Okay, so this is based on some work that we put together with Till and Frank a few months ago and some upcoming work with the same authors. So as Simon was reviewing, we would love to be able to compute these endpoint functions of these small operators, these so-called 20 primes, the smallest ones, any number of them at any coupling, like any 't coupling, any n, for any positions of the operators, right? Of course, this is too hard, although there is a lot of progress. At weak coupling, Sokachev and collaborators over many years have been unveiling new structures, computing to impressively high loop orders. And at strong coupling, we keep discovering new structures in this problem, like what Simon just explained. Even a few weeks ago, as Simon said, Vasco and friends computed the 5-point function at strong coupling. Some orders in 1/n we can do. There are some representations for weak coupling, but they are still too untractable, as lots of infinite sums and products and so on. And so this problem, maybe in a future meeting, but for now it seems a little bit too hard. Okay, so it's good for a grant application. We will compute F, C-strings talk at the end. But as it stands, it's a bit too hard. But however, as I'm going to tell you now, there is a problem, a neighboring problem that is not too hard. If you replace this O, which was y dot phi to the k, y was this null vector that Simon had, if k is large. And now we'll see what does it mean to have k large, but we'll be studying then correlation functions of these higher modes. Okay? Then it's not that hard, as I'm going to explain now. Okay, so let's go. And here are 4 operators, 4 particular representatives that we are choosing. And let's look at them, because this choice is what Frank calls the simplest correlator, because it is the simplest correlator, as you will see. So much so that at 3 level, and no coupling, 0 coupling, there is one Feynman diagram that computes this guy. So it can't be simpler than this, right? So let's see why it is just one. Because one operator is just x, one of the scalars, to some power. The other is z to some power. And the other is a mixture of z bar and x bar, z bar and x bar. 3 and 1 are equal. But then you see O2 has x propagators of type x that need to go half of them to 1, half of them to 3. And same for 4. So in the planar limit, there is one graph, which is this rectangle. So there is this frame at 3 levels, 0 coupling, and in the planar limit, that's all we have. We have this frame. Okay? It's just a bunch of propagators from 1 to 4, 1 to 2, 2 to 3, and 3 to 4. No communication between 1 and 3 and 2 to 4. So we can call these correlators cyclic correlators, because I talks to I plus 1, to I plus 2, and so on. Okay, good. Now, this is planar, 3 level, there is a single graph. What about loop level? At loop level, you see, you could put loop corrections between these propagators that connect O1 and O2. But those cancel by supersymmetry if k is large. If k is large, those propagators, they don't know that they are correcting a 4-point function or a 2-point function or a 3-point function, right? They are just in the middle of a bunch of propagators. So they only know about 2 points, so they cancel out by supersymmetry. And so, of course, at 1 million loop order, if there are 1 million propagators, they will start communicating from the inside to the outside of this picture, and then the 2 sides will not be decoupled. But as far as k is large, we have 2 types of graphs. As I said, the ones that correct the propagators between 1 and 2 and so on, they are trivial. And then we have all the Feynman graphs you could draw inside the square and outside the square. And inside and outside is the same, so it just gives the 3-level results times a function O squared that is defined in this picture. O is the sum of all planar diagrams that I draw inside the square, right? So we call it octagon. Again, why? It looks like a square, but it has these small edges, right? Of 1, 2, 3, and 4, so it's more like an octagon. And there is some reason to call it an octagon, but you can call it square if you want. So this is what gives the title to the talk. This O is the octagon, is defined here again. It's the sum of all planar graphs that I can draw inside this square that is defined like this. And that's the object. still planar, but now at all loop orders. Now, what's remarkable is that this O, okay, let me first mention the AdS picture. So this is all about gauge theory. How do we think of this from an AdS point of view? Well, a two-point function of two operators, when this number of propagators is very large, is described by a classical geodesic that goes from one point to the other. So it goes from the purple to the red point. There is a heavy geodesic going there. But then, how should we think of the four-point function? I have four propagators, consecutive ones. So they describe some geodesics that jump from here to here, from here to here, from here to here, and from here to here. And then I have the filling in of this square, inside and outside, that correspond to a string that stretches, and it's some string that has some top. It's a folded string that goes here and then folds back, and it has a top and a bottom. So it's a string stretched between some fixed classical geodesics in the bulk. Okay? So this is a fun problem where you compute an open string partition function, or two open strings. There is the top and bottom part of the fold, and they decouple. So you have to compute an open string partition function with these funny boundary conditions that we are not so used in AdS/CFT. In AdS/CFT, typically things go to the boundary. But here they end on geodesics that are inside the bulk. So we have this open string that ends on the geodesics inside the bulk, and then it has a top and a bottom. So we have this picture that this octagon square is defined as all the diagrams inside, or as this open string partition function corresponding, say, to the top of the folded string. Okay? So again, by having k large, these geodesics are classic, so they don't move, so they define this frame. But we sum over all lambda, so this folded string fluctuates. It's a fully quantum string. We have to, if we want to solve this problem exactly, we have to compute it at large Tuft coupling, where you get a minimal solution that ends on these geodesics, but at finite coupling as well, where this minimal solution fluctuates, and we need to compute the full string path integral. Now, this was done, and this octagon is known. So for the purpose of this talk, I don't want, it's a beautiful story, how we can use integrability to find this function O, but I just want to tell you that it's known, okay? We know it, it's defined by the inside of the graphs, and I want to keep it as is, because for other theories, maybe we cannot compute it, but we can still define it as the inside of these square graphs, and these combinatorics that I'm going to tell you about would apply for other theories as well. But in n equals 4, we can compute this function that's a function of the cross ratios and of the Tuft coupling. So for example, here is a plot of the octagon. I don't know if you can read. It's a plot of the octagon for some cross ratios, like 1/10, pi/3, some random values, as a function of the coupling. Okay? And there is some curve. You follow this dashed line if you want. And here it is. Okay? So this is the full non-perturbative result. For example, these lines here, you see what they are? They go close to the dashed line, and then they go crazy. So these are the results that you can compute using integrability up to 24 loops. So you have 1 loop, 2 loops, 3 loops, 24 loops. And it beautifully agrees with the curve until 1/4 where they go crazy. That's the radius of convergence of n equals 4. So n equals 4 is a finite radius of convergence. So the perturbative results try to go close to the non-perturbative, but then they go, there's no way they can pass there. And what about these lines here that go more and more and more? That's a determinant representation that Ivan Kostov, Petkov, and Serban found, where they managed to write this object as an infinite determinant. They managed to resum all this integrability computation in an infinite by infinite determinant. An infinite by infinite, it's hard to put on a computer, so what I did, I put 10 × 10, 20 × 20, 30 × 30, and then I fitted, and it goes to this dashed line. Okay, so that's just a numerical evaluation of this determinant. And this dashed line is a prediction for what this guy should be at strong coupling, which is the area of this minimal surface. And eventually, this dashed line will go there, maybe there, yeah. But it will eventually asymptote to this line. Okay. Now, this is about the planar limit. So in the planar limit, again, we have a single rectangular frame, which is these geodesics, and then we have the top and bottom of the folded string attached to these geodesics. Now, what about higher genus? Okay. So what happens at higher genus? So now at higher genus, if we call this square, this rectangle, the skeleton graph, now there are more skeleton graphs. So this is a torus, the square, the top and bottom, left and right are identified. And for example, here in this picture, you see this propagator goes up and comes down here. And there are 2 propagators connecting the purple with the green, say this one and the one that goes around using the other cycle of the torus. So in this diagram, for example, you see that you have this square here, this one here, this one, this one, this one, and this one. So you have 4 octagons. So you have 4 powers of this octagon function. What about here? Here, as indicated in blue, you have 2 powers, and then you have 2 gray that are also squares or octagons. But these gray guys, what are they? They are a sequence. You can follow one of them, and you will see that you have squares like this, where if you follow the frame, there is 1, 4, 1, 4, and 1 again. But these guys, they only use 2 operators. They only use 1 and 4. So by supersymmetry, they are trivial, these guys. So we have this Riemann surface that we quadrangulate. But when we quadrangulate, we have the non-trivial square, and we have the gray squares, which are the boring squares that just give 1. And so, for example, at genus 1, you see you can have octagon to the 0, octagon square, and octagon to the 4. So it's a polynomial of the octagon that you should determine. Okay? Okay, good. So let me make now 2 comments, which are perhaps the most technical points of the talk, and even though they are not very technical. So one of them is what we call the octopus principle. Okay? So this octopus principle is the following. Take this graph here. Remember, this was the last one, which gave octagon to the 4. But you might say, why octagon to the 4? Because octagon to the 4 means that all these squares are decoupled. But a priori, let's look just here, 1 connecting to 2. How many propagators are there between 1 and 2? K minus n, if there are n here. All I know is that I must have k propagators from 1 to 2. But I don't know that n is big such that, and k minus n is big such that they really make barriers. So why is n and k minus n big? That's just entropy. That is just the fact that there are many more configurations where they are big than when they are not big, and so they dominate. Okay? In other words, we call this octopus. It's like you put an octopus on a torus, and the octopus tries these tentacles. They try to explore all available cycles of the torus. So if there isn't a cycle that is not used, if this n was 1, that's subleading with respect to filling n a lot. And what happens then? So if I have, say, one operator that connects to another operator through n possibilities, it gives me an entropy factor of k to the n over n factorial. Okay? And that's why this octopus is called Borel, because it will in practice introduce some 1 over n factorials that have exactly the effect of Borel that Borel would have, of putting some extra 1 over n factorials. Okay? And it's a Belgian octopus, that's why it's in French. Yeah. So the punchline then is that all maximal graphs that we have, all graphs are maximal. All graphs that we need to worry are maximal in the sense that there are no more tentacles that can stretch. And they are all quadrangulations. Why quadrangulations? Because remember that 1 cannot talk to 3. So they want to stretch as much as possible, but they are quadrangulations because operator I only couples to I plus 1. Well, but then we are led to a perfect problem for the technology of matrix models, where we want to count quadrangulations. But before that, let me just mention something, which is, so we had these 4 pictures, these 4 possibilities, octagon to the 4, octagon square, and octagon to the 0, right? What is their AdS picture? So here are some pictures for what this corresponds. You see that at genus 1, you can do something fun. You can put just these 4 geodesics, and you don't put anything here. You don't put a folded string on top and bottom. Of course, this is genus 1, right? We can put our hand there in the middle. So that's genus 1. This one is also genus 1. You just have the previous solution, and then you put a geodesic here, and now there is a hole here that you can pass, right? So that's also genus 1. This one, some people criticize our artistic skills. I don't know if it's very easy to understand what this is. This is like a kitchen glove, where you put your hand, and then you cut the end. So your hand can pass there, but the sides are stitched. So it's glued here and here, but there is a hole from here to the other side. Of course, we open this so that you can see the hole here and here, but these are geodesics that are on top of each other. And so this string picture also explains why at a given genus we have a polynomial in this octagon. Here it's octagon to the 4 because it's top and bottom of yellow, top and bottom of blue. So that's it. Okay, so then what do we have to do to study these correlations at large charges? So we start, as we said, with inside and outside. Then we go to genus 1, and we have 4 squares in total. And then we go to higher genus 2, and we have more squares. So what characterizes the pictures in the first line? Well, all faces are squares because of what we said, right? They are all squares, so it's quadrangulations. And there are 4 vertices, which are our 4 operators, O1, O2, O3, O4. Good. Now let's dualize these graphs. So if we dualize these graphs, what were the 4 operators become 4 faces. You see that these graphs have 4 colors: green, purple, red, and yellow, which are the 4 operators here. And now, what were the faces that are all squares are vertices that are all quartic vertices, right? So now we have a model of quartic vertices, and we have 4 complex matrices. Why 4? Because we need a matrix A to indicate the connection between operator 1, 2, a matrix B for 2, 3, C for 3, 4, and D for 4, 1. So we have 4 complex matrices for the connections between I and I plus 1, and we have a matrix model that, if we implement it, would count automatically all genus and take into account this problem of putting these folded strings and at any loop order. Okay, so having drawn these pictures, then it's straightforward to write down the matrix model, so let's do it. So as I said, so what should we do? We have 4 complex matrices. We have some kinetic term. A connects with A bar, B with B bar, C with C bar, D with D bar, and we put some couplings here to keep track of how many connections of each type there are. So this just tells me, when I look at the connections, if I see K1 to the 5, means there are 5 connections between 1 and 2. So why do we do it? Why do we put this power? Because now imagine I have K1 to the 5, means there are 5 connections between 1 and 2. What am I instructed to do? There is this octopus principle that said if there are 5 connections, I have to put this entropy factor for the distribution of these legs. So this case will allow me to know how to control these entropy factors for this octopus principle of spreading. So basically the claim is that the 4-point function, then we have these interaction vertices, which are the quartic vertices. This line comes with coefficient 1, which are the BPS vertices, the BPS squares. And this one comes with coefficient O, which is this function of the 't-Hooft coupling and the cross ratios, which we know. Right? So we have 2 quartic vertices, A, B, C, D, and the conjugate. And we have 8 BPS vertices with coefficient 1. And what should we do? We should compute this partition function, look at the term n to the 4, because n to the 4 means 4 faces, right? We then define this reduce z, and reduce z is basically the 4-point function once we look at each power of k and do this octopus replacement, this Borel replacement, okay? So it's a very nice replacement. It makes this matrix model much more convergent than the original one, for example. It removes these divergences of the matrix model. Okay, so we could not solve this model exactly. 4 matrix models, 4 complex matrix models are not that trivial to solve. We could solve it in some limits. So let's summarize what we learned at the end of the day. So here is the correlation function we wanted, and it's a function of this zeta, which is k divided by square root of n, which is what we held fixed. So k is large, n is large, and this combination is fixed. And it's also a function of the cross ratios and the coupling through the function O. So it's a very simple function of 2 variables, xi and O. So what do we know? So one thing, we can compute it up to high genus. So up to genus 5, for example, as we said, it's octagon square, top and bottom. And then there are these polynomials at genus 1 that I discussed, then genus 2, genus 3, genus 4. Right? So at a given genus order, we can compute. We just take the matrix model and compute a few genus expansion. We could also then compute some interesting physical regimes. If this octagon function O is very small, and I want to emphasize that this is very non-perturbative. It's not weak coupling or strong coupling. It's very non-perturbative, because perturbation theory would be octagon going to 1, not to 0. Octagon being 1, remember, was the BPS ones. The ones that were trivial, they were 1. They were not 0. So going to 1 is very non-perturbative. This is the result. Okay, so this is the correlation function A. If the octagon is very large, this is the result. It's some integral of some Bessel functions. Okay? It would be very nice to find an interpolation between the two. It's probably going to be some integral with some lag R here or something inspired by these matrix models for the Wilson loops. It must be something like that. O equal to 1 is the weak coupling, free theory correlator. It couldn't be simple, just could do weak contractions, and we could not solve the matrix model. It's a bit embarrassing. Okay, so that's it, and then, of course, it will be very nice to solve this matrix model. It's a 4-complex matrix model, and we want a 4-phase contribution. That's kind of interesting, because 4-phase is, in a sense, the minimum number of phases. So if you think from matrix model technology, people typically study large n limits, where you take a matrix model and study large n. And here, it is the small n limit. If you think of n, it's a limit where n is going to 0. Now, we could simplify it a bit into 2 Hermitian matrix models and 2 complex matrix models, and then there is some other representation. This is just technical. You just resolve the quartic vertices into cubics, integrate out a few things, and at the end of the day, you get this. So what's the physical interpretation of an expression like this, where now we have 2 Hermitian matrices and 2 complex matrices, and the octagon enters in the off-diagonal propagator between these matrices? So what's the interpretation? We have 2 faces and 2 traces, right? So this is a partial dualization. We did not dualize completely, so we don't have 4 faces, and it's like 2 operators are faces and 2 are vertices. So it's a partial dualization. It's very much in the spirit of a very nice talk by Rajesh Gopakumar that very much inspired this representation. Now, of course, it would be awesome to find a matrix model that would have not quartic vertices, but cubic vertices that would describe any correlator of n equals 4 at any coupling. And based on what we know from integrability, it should be more some matrix kind of quantum mechanics with some extra degree of freedom to represent the gluing between these triangles. But it still sounds a little bit hard. We should try. We are trying. But what we can do, which is more pragmatic and realistic, is for now start with this setup where all of them are very large, and start decreasing some of them in a controllable way to start slowly approaching this, the one that we really would like, which is all of them of order 1. And so to conclude, so there is this octagon function that Frank Coronado, using integrability, managed to resum. It's a very interesting building block. It allows us to have access to an object and to resum its non-planar expansion. There is some people have there is some common law among some people that integrability is just for the planar theory. There's no such thing. There's no conceptual reason to distinguish planar and non-planar. It's the same world shit. It is just a bit of a different topology. So I think this should be demystified. Large operators are easier than small operators, but there is some progress even for small operators. And let me just finish by saying that all these recent explorations, which are related to having these skeleton graphs, so summing over skeleton graphs and then decorating them with integrability patches, is very much a realization of a program that Rajesh Gopakumar, and then there was some, for our point of view, some version which is closer to our spirit by Shlomo Razamat, of trying to understand the string moduli space as emerging from this summation over ribbon graphs of the gauge theory. So here, what we use is not just the skeleton graphs, but also integrability. So we don't go all the way to the vertices and so on. We go to the skeleton graphs, but then we fill them in with integrable patches, rather than trying to understand them even in more microscopic detail. And I think I'll conclude here. Thank you.
So, questions or comments?
Isn't it strange that the genus expansion converges?
Yeah, I think it's because, yeah, so let me, okay. I thought I was forgetting something quite important. So before I address David's question, let me invite everyone to Strings 2021 in São Paulo, and with very interesting satellite meetings in Rio and in Natal. It's good that we have these satellite meetings because I don't have enough nice pictures about São Paulo, so this is some nice Brazilian artist. I like it at least. And it will be from the 21st of 26th of June, and then it's followed by a celebration of 10 years of ICTP Cypher. Okay, so indeed, as David is saying, say if we go to strong coupling, for example, these Bessel functions that I wrote, they are given by this expression. This is this integral of Bessel functions. So that integral of Bessel function is perfectly convergent and so on, and it's this. But what is that? This is this block, which was the matrix part, which has the usual behavior that we expect from Schenker and Polchinski. But then it has these extra octopus terms that make it convergent, right? Okay, so that's technically how suddenly, because of these extra factors, the divergence is cured. Now, the basic intuition, I think, is that although we are summing over non-planar graphs, the moduli space that is higher genus is still very much under control, so it's not growing like crazy. It is just you take these folded strings and put them together and patch them together in all ways that you can glue. So So the moduli space is not growing as fast with genus combinatorically as it would if K was not very large. So I think it's an order of limit thing. So if you said differently, when we have this octopus principle, we say that the number of ways of distributing K large in 5 legs is K to the 4 over 4 factorial, right? But that's because K is large, but N is held finite. Eventually, at some very, very large genus order, we would have trouble. So if K is not taken to infinity, this divergence would show up eventually. So.
Any other questions?
Yeah, I would like to drink water.
Comments? Nope. Okay, thank you again, Pedro. So the last speaker of this session is Monica Gieke, who's talking about irrelevant current deformations and holography.
Okay, so I would like to start by thanking the organizers for inviting me to give a talk and accommodating everything. It's a very nice conference. So I'll talk about some work I've done in the past year and a half, and also in collaboration with Adam Buzowski and especially Ruben Monten, who's a postdoc at Sackler. Okay, so the motivation for this work, generally speaking, is to try to go a bit beyond the usual framework of local UV-complete QFTs. So what I mean, usually one imagines in these sort of cases is that there's some sort of ultraviolet fixed point, conformal field theory, that one then deforms by some relevant operator, and this triggers an RG flow, and somewhere along this RG flow lies your favorite UV-complete QFT. So the kind of theories that I will discuss in this talk are sort of defined very differently from that. So here one starts instead at an IR fixed point, and then adds an irrelevant deformation, and then goes into the UV. So you may say that this is sort of very ambiguous, and what am I doing? But as I will show you, actually the examples that I will discuss, in those examples, there's some sort of pre-specified way of going upwards this trajectory. And what's sort of very nice is that as one goes up, one doesn't, one can follow this trajectory, an arbitrary amount without encountering cutoff or any sickness. And another interesting thing about it is that one also never ends up in a UV CFT fixed point. So the theory is UV complete, but somehow intrinsically non-local in the UV. And some reasons to consider such theories are, quantum gravity, and as I'll explain, holography for non-asymptotically AdS spacetimes. Can I have the clock, please? Okay, so the prime example of this kind of theories are the so-called Tittybody deformed QFTs that Mark talked about 2 days ago. So these are basically universal deformations of two-dimensional QFTs in which one constructs this sort of bilinear operator from the stress tensor. It's called the Tittybody operator, and deforms the QFT action by it. And basically, the idea is that at each point, one deforms by the Tittybody operator in the deformed theory, and this specifies how you sort of go up. And this deformation is irrelevant. It's dimension 4 in 2 dimensions, but it turns out to be integrable. And quite amazingly, people have computed the exact finite size spectrum, the partition function, thermodynamics. A lot of things are known about this theory that Mark reviewed. And another interesting thing is that even though the deformed theory is non-local, with non-locality scale set by this mu, it has been argued to be UV complete. And the way to best see that is to look at the S matrix. So it turns out that the S matrix of the deformed theory is the S matrix of the original QFT times some phase factor that depends on the energy. And this is not the S matrix of a local theory, but still it's an exact formula through which this argument goes. Now, these Tittybody deformations are actually part of a larger class of deformations, which are called Smirnov-Zamolodchikov or current-current deformations, which are basically constructed from two conserved currents. At least one has a spin higher than one, and then one takes this particular bilinear combination and deforms the QFT action by it in this particular way. So these are the irrelevant current-current deformations that appeared in the title. What about holography and why it's interesting? So it's sort of important in this business to realize there are two kinds of holography that people talk about. So the first refers to these double trace current-current deformations, which I've defined on the previous slide. And these are sort of universal deformations. You can do them to any conformal field theory. And when you look in holography, because they are double trace, all you can get from them is AdS3 with some mixed boundary conditions at infinity. For Tittybody, it's mixed boundary conditions for the graviton. The way this relates to Mark's talk 2 days ago, so it turns out that these mixed boundary conditions at infinity in Tittybody for negative deformation parameter and in pure gravity, those mixed boundary conditions coincide precisely with Dirichlet boundary conditions at finite bulk radius, which is why I brought this particular picture, but this is more general. There's also been another interesting proposal discussed by this group, in which they look at a very particular realization of AdS3 CFT2 appearing in the near horizon of an AdS5F1 system, which is dual to some free orbifold CFT. And in this free orbifold CFT, they can define a single trace analog of the Tittybody deformation. So one takes Tittybody in each copy and then sums over copies. And because it's a single trace operator, when you add it to the CFT action, it actually turns on a non-normalizable mode of some field, and this changes the UV asymptotics of the spacetime. So what they get is a spacetime that's AdS3 and the IR, and then becomes asymptotically flat with a linear dilaton in the UV. And this is really interesting because it's an example of non-AdS holography. And these people compute, for example, the black hole entropy in this spacetime, which has a non-trivial Hagedorn growth at high energy, and they can reproduce it from the field theory. So that's very nice. And what's nice about this is that it shows in a concrete example that this sort of upward flows where you don't end up in a UV fixed point, but you can sort of define, they're not confined to these double trace deformations, but maybe they exist more generally, and it would be very interesting to understand how to generalize them and to track them up. So if you wish, so trying to place this talk into sort of the bigger picture, so what I'll be discussing today are these irrelevant double trace current-current deformations and how they're related to AdS3 with mixed boundary conditions and how we can do precision holography between these two. But sort of the hope is that if we manage to classify and study all observables in this duality and their precise relation, and see if there's some new kinds of symmetries that appear, and see what constraints we might have on the non-local structure of these QFTs, which we don't really understand, maybe we can somehow abstract these lessons and then use them to generalize these theories to single trace UV complete irrelevant deformations that might describe non-asymptotically AdS spacetimes. Okay, so that's sort of the motivation. So the plan of the talk, so I'll start by quickly, there'll be a field theory part that I'll quickly go over, talking about cousin of the Tittybody deformation, which is called the JTBody deformation, and I'll discuss what we know about it. And then the second part of the talk, I'll discuss holographic dictionary for both JT-bar and TT-bar, and then conclude. Okay, so the JT-bar deformation. So this is a universal deformation of two-dimensional QFTs that possess a U1 current. And one basically forms this particular bilinear from the components of this current and the stress tensor. This is called JT-bar in short. So this is a 1,2 operator. And then one specifies this upward trajectory by at each point one deforms by the JT bar operator in the deform theory, just like Tittybody. And this deformation breaks Lorentz invariance. But interestingly, it preserves half of the conformal symmetries. So the way to think about it is that this deformation is exactly marginal on the left, but irrelevant on the right. So on the left, it preserves locality and conformality of the theory, whereas on the right, the theory becomes completely non-local and so on. And this sort of structure is sort of involved. So basically, we have a CFT1, a one-dimensional CFT with some additional structure. And OK, so this deformation, just like Tittybody, it's irrelevant but integrable, probably produces a UV-complete theory. And sort of the selling points that it has, which are sort of different from Tittybody and interesting. First of all, it's easy to talk about off-shell observables, unlike in Tittybody, precisely because we have this half-conformal symmetry, so we can construct correlators of operators here. And second is that in this generalized sense, it's related to holography for extremal black holes. So I'll just flash this slide. So this is just a copy of the previous slide. So I replaced TT bar by JT bar. So one can do the double trace case, which just gives some mixed boundary conditions on AdS3 I'll talk about. But if one does the single trace JT bar deformation again in this AdS5xS5 setup, what one gets is a spacetime that's AdS3 in the IR and something called warped AdS3 in the ultraviolet. And this sort of spacetime appears universally in the near horizon of extreme black holes. So by understanding JT bar and its single trace generalizations, we hope to be learning a lot about extremal black holes. OK, so let me go on with the field theory analysis. So something that's very simple to compute in this case is the finite size spectrum. Basically, what one uses is the fact that this JT bar operator factorizes in translational invariant state. That's easy to prove using conservation. So then one puts the theory on a cylinder and considers eigenstates of the energy, momentum, and charge, and tries to see how these energies, how they vary, how these numbers vary with respect to the deformation parameter. So this equation is just basically telling you that when you slightly deform the theory, the energy changes by the matrix element of the deformation in that eigenstate. And then one uses the factorization to write this in terms of one-point function of the current and the stress tensor. And those ones, in turn, are related to the conserved charges in the deformed theory. So this is how one solves. The only unknown in the problem is the spatial component of the current. And to deal with that, we make the current chiral. And so J phi is the same as JT, which is the charge, which in turn makes the charge flow because there can be a chiral anomaly. So we also get a flow equation for the charge. Anyways, these flow equations, they basically determine the spectrum of the deformed theory universally in terms of the initial spectrum of the CFT, parameterized by conformal dimensions and charge. And this is sort of the formula. It's some exact formula. The salient feature of this formula is that it breaks down if the initial right-moving conformal dimension is too large. So the right-moving energy becomes imaginary. This is very similar to what happens for negative mu TT bar. And there's a question whether this really makes the theory sick or maybe it's still OK. So I like sort of the point of view in this paper who notes that actually JT bar has superluminal modes. And what they argue is that it's a very bad idea to put a theory with superluminal propagation on a compact space because you get CTCs, and maybe these are responsible for the imaginary energies. So as I'll show you later, if we put the theory on the plane, send R to infinity, all these sort of problems seem to disappear. And one can also do thermodynamics, and here the main idea is that since the energy levels are smoothly deformed, the degeneracy of states, so the entropy, doesn't change in the right variables. OK, so the next thing that one can compute are correlation functions. So basically here the idea is to really exploit this local conformal symmetry that one has. So has local SL2 left times this non-local side with symmetry U1. And since it's not local, we might as well just Fourier transform and label operators. So we're going to have local operators in the z direction, which are labeled by the right-moving momentum. And then the CFT1 structure completely determines the two-point functions in terms of well, so these operators have some label P, which has to be conserved, the charge has to be conserved, and then the only information here is the conformal dimension of this O. And similarly, the three-point function is completely determined in terms of these H's and an OPE coefficient. And sort of the novelty here is that this OPE data, this conformal data, they can be arbitrary functions in principle of this combination mu times p bar, which is the only Lorentz invariant combination. But anyway, since this is CFT1, the idea is that if we know these functions exactly, we can completely specify the theory, and these functions can, in principle, be computed to all orders using conformal perturbation theory. So now let me show you, actually the conformal dimensions, it's easy to compute them because I just showed you how to get the spectrum of the theory on the cylinder. And for example, if we had the CFT, we know the spectrum on the cylinder, we also know the conformal dimensions on the plane by using the exponential map. Here the story is a bit more complicated because we only have one copy of SL2, and actually this is broken by the cylinder identification. And in order to restore it, we basically need to perform an infinite boost to move the identification on only the null coordinate and then perform the exponential map. And at the end of the story, we get just an exact formula for the conformal dimensions and charges and how they depend on this mu p bar. So you see it's quadratic and this is linear. And from this formula, there's no obvious pathology, so it seems that the theory on the plane is fine. And another cute thing about this formula is that it looks like spectral flow. So if I do h minus q squared over k, it's constant, it's p bar independent. So this looks like, a bit like spectral flow with momentum dependent parameter, which might have an interesting interpretation that I don't know so far. Another thing that one could study is operator mixing. Which usually is a hard problem, but here is tractable because the deforming operator is so simple. So when you compute deformed correlators, you just bring powers of this JT bar, and the correlation functions with the other operators are just determined by the word identities. So it's doable. So basically, for most operators, all the mixing happens within the X Virasoro block. So what I mean, you have to go to this mixed position momentum basis, and to do that, so if you take some operator in the original CFT, it transforms into representations of Virasoro left times Virasoro right. You have to decompose this Virasoro right into global SL2R blocks, and then do the Fourier transform. So this is how I write the various global right-moving primaries I get, and only these guys mix among each other. So you can track that down. Another thing you could try to do is compute the OPE coefficients and you know how how they change with mu p bar, and that's a little bit of a subtle calculation, but some sort of indirect calculation that's work in progress with Alessandro Bombini and Andrea Galliani, who are in the audience. So we show that if we assume that the OPE coefficients are completely undeformed, this is completely consistent, so all we have to show that this is the only choice. And once we show that, so if we show that, basically we'll have all the correlation functions because we know all the OPE data. Okay. So that was the field theory part of the talk. Now let me talk about holography. Okay. So as I said, all these current deformations are double trace deformations, which are known in holography to correspond to turning on mixed boundary conditions for the dual bulk fields. So just to remind you, if we have, for example, a scalar field, like a bulk scalar, so usually, in usual quantization, there's some non-normalizable mode, and its coefficient corresponds to the source in the dual CFT, which is fixed. And then there's some normalizable mode, And this coefficient corresponds to the VEV, expectation value in the dual CFT, which fluctuates. Now, if you turn on a double trace deformation, you get mixed boundary conditions, and the simplest way to see that is by looking at the variational principle. So the variation of the deformed generating functional is the variation of the original CFT action minus the variation of this O squared double trace operator. So this guy is VEV times delta source, and this is just delta of O squared. And then you try to rewrite this thing as some new VEV times delta of a new source. And here the new source is just this. So you see, so in the deformed theory is this guy that you're keeping fixed, which in terms of the original bulk field means that you keep a linear combination of J and O fixed. So that's the usual story. And I mean, it's a very simple idea. The idea is that for all this double current deformation, you just do the same blindly. So for JT bar, so in order to play this game, we need to introduce sources for the two operators. So J, we couple it to a boundary gauge field, and the stress tensor, we couple it to a boundary field bind because it's not Lorentz invariant. Then we need to covariantize this JT bar deformation, which is basically done like this. So the coupling becomes actually a null tangent space vector. And then we look at the variation principle like we're looking here. So this is the variation of the original CFT action. And then we put delta of the deformation, and then try to write it in some form that looks like new sources times delta, VEVs times delta of the new sources, and equate what's inside the delta and what's outside it independently. Okay, so doing that exercise, this is what we find. So the new sources are the old sources minus mu times the expectation value of the other operator, and these are the new VEVs. Okay, so I should say, so this was just a large field theory argument, basically equivalent to doing Haber-Stratonovich. Now, if I want to do holography, I have to tell you how these things are extended into the bulk. And to extend into the bulk, so the stress tensor is modeled by 3D Einstein gravity, and this chiral U1 current is just modeled by a U1 Chern-Simons gauge field in the bulk, both of which are non-dynamical. So basically what I'm getting is this theory with this funny boundary condition, keeping this E tilde, A tilde fixed. If we want to do holography, so now we write down the most general bulk solution. We read off the expectation value J and T just using the usual AdS3CFT2 dictionary. And, it was there. Oh. Okay, I'm very far behind. Okay. Okay, and then plug it into this formula, in this ugly formula, and then that thing turns out to match precisely with the field theory calculation I showed before. So this really works very nicely. One can also look at asymptotic symmetries that preserves these boundary conditions. And interestingly, what one finds, so the left-moving symmetries are the SL2 I talked about, and also the current are left-moving. And this expectedly get enhanced to Virasoro-Katsmuti. But the surprise is that the U1 symmetry that was on the non-local side, it gets enhanced to a Virasoro. And this Virasoro is sort of funny. It's non-local, so it depends on this combination of coordinates. It's non-local, and it depends on the background fields. I don't know what this thing is supposed to mean in field theory. But the only thing I can point out is this looks different from the field theory structure I was getting before, because before the T-bar operator, which sort of generates this U1, had non-trivial charge, anomalous charge, and anomalous dimension, so it wasn't commuting with this, whereas here in the asymptotic symmetry group, they commute. So we get something slightly different and slightly different organization of the theory. Okay, so in the last couple of minutes, let me talk about TT-bar. So the idea is that we try to apply exactly the same thing to the TT-bar deformation. So we look at delta SCFT minus delta STT-bar, and we try to write it as new VEV times delta new source. And doing that, we get these flow equations for the metric and the stress tensor. And it's good to introduce this T hat, which is T minus the trace. And the solution of this flow equation is really trivial. T hat is linear in mu, and the boundary metric is quadratic. So this is the new source, and this is the new VEV of T hat, and this formula works for both signs of the deformation parameter. You can have as many VEVs of other operators turned on. and it only uses Lagrange field theory. So no holography so far. If I want to do holography, I need to extend this into the bulk using the Fefferman-Graham expansion, which looks like this. And here, so remember here, gamma and t hat were the boundary metric and the stress tensor in the undeformed CFT. So I have to identify this with G0, and this guy, it turns out the wave of t hat is nothing but this coefficient in the Fefferman-Graham expansion. So generally we get some ugly mixed nonlinear boundary condition by doing this replacement here, but that only depends on the asymptotics. If we want to add matter fields, we can add them to the variation equation, and their boundary conditions are unchanged. Okay, so something actually nice happens if we're in pure gravity. Because in pure gravity, the Fefferman-Graham expansion actually truncates to the next order. And then we notice that these mixed boundary conditions that we're getting at infinity, they coincide precisely with the Dirichlet boundary conditions when we set this rho to be proportional to mu. And this is how we recover the proposal by Mark and the collaborators. And we also find that the deformed stress tensor, which is given by this formula, precisely coincides with the Brown-Young stress tensor with some particular counter term at this cutoff, quote-unquote cutoff surface. If we want to measure the energy of this configuration, so we can match it perfectly to field theory. So basically, the idea is the phase space, in the phase space that we have to make the metric on this surface flat. So we compute the energy using the usual formula, and then we try to write a formula like this in terms of the energy of the undeformed state. And how do we know which undeformed state corresponds to this black hole? Basically, we can measure the horizon areas because we know that the degeneracies are not affected. And it's a very cute technical point that actually Magao et al. They did a slightly different calculation. They computed the energy on a cutoff surface here at Schwarzschild coordinate equals to mu. Which looks like a different value of the radial distance than we do because we have Fefferman-Graham coordinate equal to mu. But if you're careful about which phase space you're working in, actually everything works perfectly. Okay. Then, if I may take another minute. However, in presence of matter, this whole nice picture completely falls apart, and there's no more relation between Dirichlet at finite radial cutoff and these mixed boundary conditions at infinity. And this makes sense because the fact that we have a universal formula for the energy in Tittybody deformed CFTs should map to some universal asymptotic behavior in gravity. So it can only depend on the asymptotic behavior of the metric at infinity. And we also find Virasoro symmetries here that we don't understand from field theory. Okay, so let me just leave you on the summary and future directions, and thank you.
Questions or comments?
Could you describe how the Virasoro symmetry comes about?
I mean, it's just an. Thank you for the question. So basically, we have this phase space. So we define this phase space where we keep this particular combination of metric components. So this is G0 and this is G2 fixed. We have to characterize the most general diffeomorphism that keeps that boundary condition fixed. These diffeomorphisms are horribly background dependent, and we have to compute the charges associated with them. There's a lot of algebra, tons of cancellations, and in the end we find, these diffeomorphisms depend on this state-dependent coordinate, little u and little v. So these are the state-independent coordinates in the Tittybody deformed CFT, and on the background field. So it's some sort of complicated formula that determines this u and v. But everything in the end just depends on either u or v, and we find two decoupled Virasoros that depend on this. But these are neither left-moving nor right-moving, I should say, this u and v. And the fact that they're decoupled is It's very, very non-trivial. There's huge amount of cancellation, and they also have the same central extension as in the usual original CFT. So it's really like a non-local deformation of the original Virasoro. I don't know what it means in field theory.
Yeah, concerning single trace irrelevant deformations and holography, there was a story over 20 years ago about the full three-brane metric, how that corresponds to a dimension 8 operator, a single trace dimension 8 operator.
Yeah, so to my knowledge, of course that goes, as you said, that goes very much in that direction. And to my knowledge, Leonardo Rastelli was trying to make sense of that flow. You can view this Kutasov and collaborators work as like a baby AdS3 version of that, but I guess yeah.
Yeah, the interesting thing there is that far in the UV you get flat space, so maybe it could lead to another version of flat space holography. But
yeah, so to my knowledge, Rastelli is looking into it, but.
Okay.
So these non-localities that you get in the deformed theory, what implications do they have for the bulk? Or
well, so basically, the way that they're realized in the bulk, so you're basically just having AdS3 gravity with all the fields that you had before, and you're imposing these mixed boundary conditions. Those mixed boundary conditions are responsible for the non-localities. So it's very funny. So all you're doing, you're just slightly changing the boundary conditions for the metric, and I wouldn't say all hell breaks loose in the boundary field theory, but it becomes completely non-local from just a change of boundary conditions in the bulk.
Nothing in the bulk changes in terms of local properties.
Well, for that you need to really study 1/n corrections to this. And maybe it can be done because this Tittybody operator actually factorizes in arbitrary states. You don't need a large n. But yeah, that needs to be studied beyond n equals to infinity.
Right, so maybe we should wrap up for the day and thank